So we're going to cover exponential functions. And exponential functions are used when you're trying to find growth, also decay, investments, model populations, and interest. The function is going to consist of multiple parts. The first part is the a and b. A and b can be rational or irrational numbers, and they are going to be raised to a power, and that is your variable. This is the difference when it comes to other equations. When we were dealing with polynomials, you have a leading coefficient and you always have a variable as your base. In this case, your variable is going to be your exponent. That's why we call it exponential. We need to make sure that a is not 0, so it has to be a number other than 0, and b is a positive constant, but it cannot be equal to 1. So it could be a decimal, it could be 1/2, 0.123, right? That works, but you can never have a b equal to 1. So exponential growth happens whenever a number or quantity increases by the same amount over a certain interval of time. One of the biggest differences here is that compared to other functions, this increase is going to happen in a very short period of time. So numbers are going to get larger very, very quickly. The exponential growth formula is y equals a, and a is going to be a constant plus 1, and that's always going to be the case, plus a specific rate, and t is going to be the time. So this is the formula. You need to make sure that with the information given, you can plug it in and you're able to solve for the missing parts. Your y is going to be your total amount. Your a is going to be your initial amount. And the rate of growth is going to be a decimal. In the problems, you may get 3%, 4%. So you need to make sure that you are changing that percentage into a decimal. And you also have to be careful with the time. Some problems are going to ask you for do things per month or per year, and you have to make sure that you're plugging in the right number. For this problem, we have to write and solve an equation to determine the balance after 25 years. So we're going to get the information and then we're going to start making notes. So we know that our time is going to be 25 years. Your initial amount, because it tells you your initial investment, is going to be 18,000, and this is going to be a 3% increase. 3% is 0.03. So that's going to be 3% interest. This is the part where you have to be careful. It tells you annually. So this is going to be easy because we only need to put the 25. If this was quarterly, then you will have to multiply the years times how many times per year. But in this case, we're just going to put y is equal to, again, we have a 1 plus r t. So y is equal to 18,000 times 1 plus 3% over 25 years. And you can just put that in the calculator. Your answer is 37,688. And in this case, your decimal point is 0, 0.027. But because we're talking about money, we only have to round to 2 decimal places, and that will still give us 0.00. So we don't need to write it down. That is our answer. In this case, find the annual interest rate. And now we're looking for R, not for the total. So we're going to make sure that we label everything properly. It tells you that the amount of 15,000 grows to 15,525. So that means that your initial amount, your A, is going to be equal to 15,000. Your total, your Y, is going to be equal to 15,525. And it tells you that in the first year, and then, so this is year one, and then in year two, we have 16,068.38. And this is in year two. The time that this took was 2 years total. So yes, it increased 1 year and then increased again the second year, but we know that it took 2 years total. So even though that we got the first year and the second year, we're going to use the second year, the total. So in our formula, we're going to plug it in as 16,068.38. And this is going to be equal to your initial amount, which is 15,000. And then you're going to put times 1 plus our R that we don't know. And then you're going to put your exponent of 2 because it took 2 years. And then we need to work backwards. So I'm going to divide both sides by 15,000. That is going to give you 1.071225. In this case, we're going to put multiple decimal points to make sure that our answer is as accurate as possible. And that is going to be equal to 1 plus R squared. So we're going to find the square root of this. And that is going to be 1.035. And then we have multiple zeros after that. So in this case, I'm going to round, and we have 1 plus R, subtract 1. So we have 0.035 is equal to our rate. So that means that the interest, the annual interest, is going to be 3.5%. Exponential decay is when a number or quantity is going to be decreasing by, again, the same amount over a certain interval of time. It could be a couple years, it could be a couple months, or it could be many. The formula for decay is similar to the growth one, but again, the only difference is going to be your sign. You're going to be subtracting the rate of change. So you have your total, you have your initial amount, you have the time, and you have the rate of change. So with exponential growth, you can actually see how bacteria spreads quickly. But with decay, you're going to see how you have some elements that do half-lives. So this is a lot used in chemistry. For example, 3, we have a new car is purchased for 25,000. It depreciates 12%. you need to write the formula, but you also need to figure out how much is a car worth after 4 years. So we are going to put that A is 25,000. Your time is going to be 4 years, and the percentage that is dropping, your rate is going to be 12%, so 0.12. When we put into our formula, we're going to be looking for our y value, what our total is going to be, and we put 25,000 1 minus 0.12, and this is going to be over 4 years. And now you just plug that into the calculator. Your answer for this problem is going to be y is equal to 14,992.38. Even though that this is 0.384, the 4 doesn't round it, so we're just going to keep it as 0.38. So your car would be valued at that number. So if you were trying to sell it, that's the most people will give you for that car. For example, for you have a van that has been converted for a wheelchair, and is telling you that the original price is going to be 7/8 of the previous year. So in this case, they're not giving you a rate that is dropping by, they're telling you how much this car is going to be worth. So your initial amount is going to be 49,810. Then we know that this is going to be taking place over 6 years. The amount that is depreciating is actually an eighth. So it's dropping an eighth of the value. So we can actually rewrite this problem slightly different than the previous one, because we can write it as 49,810, but the 1 is actually 100% of the value, and the rate that you're adding or subtracting is how much is dropping. So in the previous problem, you had a 1 minus 0.12, which is the same thing as 0.88. So instead of finding that percentage and do 1 minus 1/8, we can actually just use the 7/8 that is going to be the value of the car. That is the same thing as saying 1 minus 1/8. And then this is going to be over 6 years. And we're going to just plug that into the calculator. And then after 6 years, our answer would be 22,354 with 49 cents. The decimal after the 49 is a 4, so we're going to keep it as 0.49. And that will be the answer after 6 years. So in this one, we have an exponential growth problem. We have the time that is going to be 14 years. We have your initial amount. We have your interest. But the thing that changes is going to be compounded quarterly. So in every single year, we're going to multiply it by 4. So when we set up the equation, we're going to put y is equal to 21,000 times 1 plus 0.04. And even though it's 14 years, you're going to put 14 years times the 4 times that it happens during the year. So it happens 4 times during the year. That is a quarterly part. And then we multiply that by 14, the number of years. So our answer is going to be y is equal to 18836.07 65. So we're getting 188,836.65. And the reason that we're getting so much more money than the 25 years previously is part of it is the interest, but it's also the number of times that it happens per year. This makes the exponential function much, much larger.